So today we're going to start with what's called proof by induction or induction proofs. It doesn't matter how you say it. Now, all types of proofs can't be used on all types of problems because it depends on the nature of the problem. So a contradiction proof, for example, is when it's very difficult to prove something is true going forward. So we start by assuming it's false and we go backwards. There are things like that. If it's something where I'm dealing with spatial geometry and it's really complicated, I might be doing a multi-dimensional epsilon delta proof, which is, by the way, the most scary thing you've probably ever seen. But if I'm trying to prove an algebraic formula is always true, it turns out induction is one of the cleanest ways to do it. So in really simple terms, what induction means is you make an assumption that something is true for a certain case, and then you show that assumption leads to it's always true for every additional case. Now that's kind of going out there on a limb. You're saying, wait a minute, if I assume something's true, doesn't that make it true automatically? Well, if you assume something's true for a particular case, that doesn't mean it's always true. It means it's true for that case. Then you show algebraically that leads to it's true for the next case, and then the next, and the next, and the next. So the way we do it, we have a formula. Let's say we have a formula. We have a formula for n, where n is a counting number, probably. N could be 0, n could be 1, 2, 3, 4, 5, depending on where you're starting, but n is generally going to be a natural number. Okay, I can start with 0. Usually you don't think of it as starting as a negative. So think of it as n being an index, like in a summation or a sequence, that type of n. So I have a formula with an n in it. What we do is we show it's true for the very first case. And what the first case would be, if n is starting at 0, then we show it's true when n is 0. If n is starting at 10, then we show it's true when n is 10. For the very first case of n, we have to prove it's true for that one. And by the way, that's always the simplest part. That's trivial arithmetic almost 100% of the time. So I start with that because I have to have something that's true. Then what we do, and this is the biggie, we assume it's true for n equal k, where k would be an integer down the road. So let's say that n equal 1 is my first case. Now I'm going to assume it's true for n equal k, and that k would start with 1, but it could also be a million. And then I'm going to show that that assumption leads to being true for k plus 1. And that's, again, it sounds kind of odd. It sounds like we're assuming what we're trying to prove. No, it is not possible to prove a false statement is true using induction. A lot of people think it is. It is not. You would always come up with a contradiction. It isn't. There's no way you can prove something false. But if something is true and it's in a formula situation, it's very difficult sometimes to derive big formulas. And you're saying, how do I know this is true? I'm plugging in numbers and it seems to always work, but that's not a proof. So induction, again, we show it's true for the first case, we make this assumption, and then we show that leads to this. And we're going to do a few examples. And the types of problems we do typically are going to be things like summations and products, like the capital pi, things that lead to really nice formulas. So let's go back in Calc 1, when you were first remember doing summations to find areas under curves, you added up all the areas under the rectangles, all that kind of stuff. You learned a few very simple formulas. The sum from I equal 1 to n of 1, is n. The sum from I equal 1 to n of I, that's 1, 2, 3, 4, 5, right? That one's n plus 1 over 2. That one's actually really easy to derive. But then when you get to the higher ones, this one here is n plus 1, 2n plus 1 over 6. And then the only other one you ever actually really need or ever really use is this one, which is just the square of this one. Okay, these are summation formulas that are very, very useful. This one is very easy to derive. Sometimes it's referred to as Gauss's formula. Okay, but to derive this and to derive this, I mean, think about that for a moment, how ridiculously difficult that might be. I'm saying that 1 squared plus 2 squared plus 3 squared all the way up to n squared for any n greater than or equal to 1 is equal to this. But how do you take something that looks like that and get this? Again, whoever figured this out, it was genius, but I don't want to have to derive this from this, but I can prove this using induction. So that's what we're going to do. We're going to start with this one because this is beautiful. And by the way, this one is on your quiz. So here's how it's going to work. We're going to use induction. We want to prove that the sum from I equal 1 to n of I squared is equal to n plus 1, 2n plus 1, all over 6. I want to prove this. Now, what I always tell people to do in a situation like this is convince yourself that you actually believe it's true first. And I think I've used this analogy before, but I absolutely believe it is impossible to prove anything that you don't believe is true. You'll spend all your time trying to disprove it. My Calc 3 class recently had a quiz where they were doing the limits in in 3 dimensions for the first time. And I had people trying to prove something was false that was actually true, and trying to prove something was true that was actually false. They kind of missed the point, and they just beat their heads against the wall trying to come up with examples when it's like, no, you're on the wrong side. So let's just say n is maybe 4. So if n were 4, then I've got 1 squared plus 2 squared plus 3 squared plus 4 squared. That's 1 plus 4 plus 9 plus 16, which would be what, 30. All right. Now, if I put a 4 into this formula here, I'd get 4 plus 1, 2 times 4 plus 1, all over 6. Well, that'd be 180 over 6. Oh my gosh, I got the same thing. Well, of course I get the same thing. It's a formula. But I always like to do this little quick double check just to make sure I didn't write the formula down incorrectly, or that I actually understand what the formula is doing. You see, I can always do this, but what if my n is 1,000? I don't want to do this for 1,000. I want to do this. It's easy. So the induction starts like this. There are 3 stages, and only one of them really requires any work, but all 3 are critical. So the first stage is prove n equals 1. Why? Because I'm starting at 1. So my first case is n equal 1. So on the left side, I equal 1 to 1 of I squared is just 1 squared or 1. When n is 1, the left side is equal to 1. The right side, 1 times 2 times 3 over 6 is also equal to 1. The left side equaled 1, the right side equaled 1. So I can say this equals this. They both equal 1, right in the middle. Beautiful. That's trivial but critical, because if the first one's not true, then the formula is not true. But you still might be able to derive something with the original assumption that you're going to make now. That's where it's dangerous. So second step, assume true for n equal k. This is called the inductive hypothesis, what I'm about to write. I'm going to assume the following is true, that I equal 1 to k of I squared is k plus 1, 2k plus 1 over 6. I'm going to assume that statement is true. Well, aren't I done then? No, I need to show it's true for all n. I'm assuming it's true for one value of k. Not any particular value. I'm just saying, I'm assuming it's true for that particular value. Now, the next part is we need to prove, I'm just going to shorten, we need to prove that case. So what we're going to do is we're going to write down the sum. I equal 1 to k plus 1, right, of I squared. Well, what is that? Well, wouldn't this be, right, like this? Now stare at that for a moment. I want you to add up the first k plus 1 perfect squares. Well, wouldn't that be the same as adding the first k perfect squares and then adding the k plus first perfect square? Yeah. This is equal to this. forget the formula. This statement is absolutely equal to this statement. There's no question because I just did one more term. Okay, so now I'm going to use my inductive hypothesis. I assumed this was true, so I'm going to replace this with this. And then I will add that term right there. And hopefully I left myself enough room. So here's how it works. If this statement right here is true, we're assuming it's true, but if it is actually true, then absolutely this is equal to this. If this is true, then this is equal to this. So now what I need to do is manipulate this quantity so that I get the formula that I need. Right now, this does not look anything like that. Not yet.
So what happened to the denominator?
Did I lose the denominator? Oh, thank you. Yes, sorry. That'll make it harder to prove if I leave that out. Good catch. Now, how the heck am I supposed to do this? Should I multiply this out? Actually, no, I don't know that you want to multiply it out. Maybe factor it, or common denominator might be a better way to go. Make this one big old quotient. Why? Because the final version probably needs to be in a quotient form. So if I make this one big old quotient, then this will be what? It'll be k plus 1, 2k plus 1 plus 6 times the square of k plus 1 all over 6. I'm going to wrap that around. That's equal to this. Okay. Now, clearly, I have a k plus 1 in both. So why don't we factor out that k plus 1? I might have to go back up to the top in a minute. And what will that leave me on top? Well, that'll leave me with a k and a 2k plus 1. And over here, it'll leave me with a 6k plus 1. And then all of that is over 6. So hopefully everybody sees, just that's simple algebra. Now I am going to, sorry about this, but I need to erase this because I need the space. Now, I'm not worried about that. I'm not worried about that. We need to manipulate this. So let's do a little algebra. If I said k times 2k plus 1 plus 6 times k plus 1, well, if we multiply this out, what do we get? We get 2k squared plus k plus 6k plus 6, or 2k squared plus 7k plus 6. Okay, I believe that's factorable. And let's do this. So what does that look like it's going to be? Probably a 2, there we go, and a 3. Does that look about right? This quantity looks like that right there. Beautiful. Okay. Let me go ahead and now erase this line. We're just about done. And we're just about done. How could we be just about done? Because now I can rewrite this quantity right here as what? As, actually use a different color here. That quantity right there is k plus 1 times this, times k plus 2. See that guy right there? What if I wrote that as, well, actually, I'll leave it like that for a moment. 2k plus 3 all over 6, or k plus 1, k plus 1 plus 1, 2 k plus 1 plus 1 over 6. Now we are finished. So we're finished. How are we finished? Because this is the formula, the n plus 1, 2n plus 1 over 6. This is the formula for this if I replace n with k plus 1. Now notice we never messed with this formula here to come up with this. No. Our induction hypothesis only dealt with that term. We didn't assume anything about k plus 1. But by assuming this met the formula, basically, and now I added the next term, I got the formula that I would have gotten with the next term. Now, this algebraically, this might seem a little bit messy, but I mean, the hardest thing you did was factor a quadratic. So no, the algebra is not that bad. But what's beautiful is look at this formula. It's exactly this formula with n replaced with k plus 1. That means we are now finished. We have proved it's true. So most of the work is going to be proving the last step. It's not always a lot of work. In this case, I froze there for a second. In this case, it's a little bit of work. All right, let's try another one. When you do a few of these and they work, it's kind of beautiful. Now, obviously, when you're doing this on a piece of paper, you use as much room as you want. I just don't have a lot of room here. I want to prove, let's see. We'll do another summation one. I can't read. 1 over I plus 1. I want to prove that this equals this. Now remember, you do not have to specify what I is. In a summation, not only does the index have to be an integer, it has to be an integer that increases by 1. So it means I equals 1, then 2, then 3, then 4. You don't actually have to lay that out. That's how we define summations. So clearly, I'm only inputting integers, and n has to be an integer. N couldn't be anything other than an integer greater than or equal to 1. It's not possible because that basically contradicts the definition of a summation. So let's put in maybe I don't know, let's go 3. So if I went the sum from I equal 1 to 3 of 1 over I plus 1, what does that give me? Well, that'd be 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. I don't want to go too big because it's too much algebra. Well, let's see, that would be 6/12 plus 2/12 plus 1/12. That's 9/12 or 3/4. Okay, great. Now, according to this, I'm supposed to get, if n equals 3, I should be getting 3 over 4. I did. Okay, I've just convinced myself that isn't a proof. But by just picking an arbitrary value and I got the right answer, okay, I'm pretty sure this is correct. I'm pretty sure I wrote it down correctly. It's probably more accurate. Again, trying it for one example doesn't prove anything, but if somehow this didn't work, then I would question whether this was written correctly in the first place. So let's do this. This should be relatively simple. So we'll start by prove n equal 1. And again, since it's starting at 1, I go 1. If I'm starting at 0, then I go 0. If I'm starting at 7, then I go 7. Most people make the mistake of saying your first step is always prove n equal 1. No, your first step is prove n equal whatever the first value in your formula is. In these first two cases, that happens to be a 1, but it's not always going to be a 1. So that means that I equal 1 to 1 of 1 over excuse me. If I replace this with a 1, I'll get 1 over 1 times 2, which is a half. If I go over to here, and if n is a 1, this does equal 1 over 1 plus 1. See, I got different ways. This was 1 times 2. This is 1 over 1 plus 1. But in either case, I got the same thing. Okay. Again, that one should always be easy. Second step, which should always be easy, assume true for n equal k. In other words, we will assume that the sum of the first k of these is k over k plus 1. This is our induction hypothesis. And a lot of times when we're explaining why something is true, we'll say things like, by the induction hypothesis, boom. Okay, I'm assuming this is true. I don't have to prove that. Now, we want to show. So now what I'm going to do is say, if I asked you to do the sum of the first k plus 1 of these, you do not replace this formula with k plus 1. That's what you're supposed to conclude at the very end of the problem. So I know I am done when I have proved that this equals k plus 1 over k plus 1 plus 1. That's when I'm done. I can't start by putting it in because then I would be done. I've concluded, in fact, I'd be assuming what I'm trying to conclude. No, what I'm going to do is take my inductive step and then just add the next term. So this must be exactly that plus whatever this formula would yield at k plus 1. Oh, okay. So again, I'm going to add up the first k, which I already have, and then I'm going to do one more. So this would be 1 over k plus 1, k plus 2. I'm assuming this is true. Therefore, if this is true, then this is absolutely guaranteed to equal that. What I need to do is make that look like that. That's my goal. That's where the algebra comes in. I can't assume this. I have to conclude this. So when I'm looking at this going, well, again, I think common denominator might be a good goal. Okay. Looks like I need a k plus 2 over k plus 2. Okay. So hopefully everybody sees that.
Wait, Professor, is that a sum or is that a product in the denominator? Like, is it n over?
You're talking about here, or where are we looking?
I'm sorry, I might just be a little bit confused. I'll
assuming,
try.
well, no, I'm assuming this. I'm assuming this. That's that piece right there. I'm adding one more term, so I'm taking this, I'm adding it to this. Now I just want to put this over a common denominator. So that's what that is.
Is it n times n plus 1 or? I'm sorry. Never mind.
There's no n times n plus 1 anywhere in the problem. I'm not sure.
Never mind. I'm sorry.
Clean off the screen, maybe. By the way, guys, I do want you to ask questions if you're at all confused, because this is I don't want to say it's an algorithm, but it kind of feels like an algorithm. After you do 2 or 3 problems, you go, these kind of all have the same feel. Well, every problem's different, but the order of things is always going to be the same. And the k plus first term is 1 over k plus 1 times k plus 1 plus 1. That's what the k plus first term is. That's what that is. Okay. The first, if I do this again, right here, what I have is the sum of the first k plus, I write k plus first term. How about if I write like that? The sum of the first k plus 1 is the sum of the first k plus the k plus first term. That's the sum of the first k. That's the k plus first term. That kind of give yourself a reminder of what you just said. Now, the rest of this should be relatively simple, because look at the numerator. That numerator is k squared plus 2k plus 1, k plus 1, k plus 2. But isn't that k plus 1 quantity squared? Ooh. And I can clearly cancel k plus 1s. By assuming this was true, and now adding the k plus first term, I got this. What is this? This is the formula for n equal k plus 1. That means we're done. We got this formula with n equal k plus 1. We didn't start by assuming it. That was our conclusion. So now we know we've done it correctly. Okay, so that's a simple induction proof for sums. I want to do a different version of it, because again, I want you guys to get kind of a feel for this. These were purely algebraic. I mean, there's just nothing conceptual about this. And it's kind of nice. That, we like these because there's nothing hard about them. Induction proofs can be hard. I don't really want to go there yet. Okay, so let me try another one. Let me grab one. I had an idea of one in the textbook. Just gotta be able to see it. Sorry, kind of. Oh, here it is. Here it is. Boy, it's so dark in my room here. All right, so I'm going to do it without using the summation. Okay. Hold on a second. Oops. Give me 1 second. I lost my place. Hold on. Where? Oh, there it is. Okay. Pardon me for a moment. My page flipped on me and I can't find the problem. No wonder I was on the wrong page there for a second. Okay. Where is the form? There it is. Let's say. This is the one I want to do. All right, I've got something that looks like this. Where is it? Oops. Equals. Okay. This one is different from the other one we just did for many reasons. One is I didn't start off with a formula. I don't have a summation. But this is also a product. Now, I would like to work backwards and write the actual product, but sometimes you give them a formula that looks like this. So 1 minus 1 over 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, forever and ever, all the way up till n squared. N is starting at 2, obviously, and is not starting at 1. Why isn't n starting at 1? Well, because if I did 1 minus 1 over 1 squared, that would be 0, and the whole thing would be 0. That's not a very interesting problem. If I wanted to write this in a formula sense, this would be product I equal 2 to n. That means that n has to start at, right? The smallest n could be would be 2. What would this look like? This would be 1 minus 1 over I squared. So if I said, what is this? This is actually what it is. But in this case, I didn't start off with the actual product formula. I started off with the terms. There's nothing wrong with that. In fact, a lot of people would prefer this because I can tell exactly what's going on here. So let's do the induction. So
Professor, in that first line, is next to the n is greater than or equal to 2, is that an I or is that a
semicolon?
Okay.
Semicolon. Yeah, that mathematically, that's actually the only symbol you can put there. You wouldn't put a period and you wouldn't put a comma. It's kind of a, yeah, I like using semicolons mathematically because they're easier. Yeah, except my semicolons sometimes look like I's. I get that. Not a good semicolon. All right, so what do? Well, we start with this guy. So we don't start with n equal 1 this time, we start with n equal 2. So show n equal 2. All right, so if n equals 2, that means I only have one term. Then 1 minus 1 over 2 squared. Well, what is 1 minus 1 over 2 squared? That'd be 1 minus a fourth, which is 3/4. Over here, if n equals 2, I have 2 plus 1 over 2 times 2, which equals 3/4. All right, big check. I'm a big fan of say yes. On the left side, we calculated, we got 3/4. On the right side, we calculated, we got 3/4. So the formula is true in the first case. Okay. Now, here's why he's saying, if I assume it's true for n equal k, all I have to show is that that automatically means k plus 1. Well, why do I only have to show that? Because if assuming it's true for k guarantees it's true for k plus 1, and we've already shown the first instance at 2, that means that if k is true, assuming k is true guarantees k plus 1 is true, well, that means then I've proved n equals 2 is true, so that would mean that n equals 3 has to be true. But then that would mean n equals 4 has to be true to infinity. That's why induction works. If 1 leads to everything that follows being true, and you have the first case being true, then everything that follows has to also be true. It's beautiful. It's not circular reasoning because you have to show something's true. So now we are going to assume this. Okay, and now we need to show, and I'm kind of abbreviating. What I'm saying is you have to show this is true for n equals k plus 1. I just don't have a lot of board space. Now, how do I do that? I'm assuming this is true. So what I'm going to do is to this quantity, I'm going to attach the k plus first term. Okay, I'm assuming that this is equal to this. So what if I now multiply this by the k plus first term? Wouldn't that be equal to taking this and multiplying it by the exact same term? So if I'm assuming this is true and I simply multiply both sides by this, then that's got to be true. So I'm done with the left side. What I need to do is manipulate the right side until it looks exactly like this formula here, but with n replaced with k plus 1. Now I can't make it work. If this formula were not true, then it's an absolute impossibility that I could manipulate this and have it look like that. Can't happen. Okay, it can only happen if it's true. Well, that's kind of icky looking. So let's mess around with this, and eventually we're going to need common denominator and all that kind of good stuff. So that right there is going to be what? That's going to be, let me write it as k plus 1 squared minus 1 over k plus 1 squared. Now, the reason I like this, there's a lot of things. The top is going to be easy to manipulate, but you notice right off the bat, I can do that. That's a good thing. Now, what else is true on top? Well, k plus 1 squared minus 1. That would be k squared plus 2k plus 1 minus 1. On the bottom right now, I have 2k, k plus 1. Okay. So now on top, I have k squared plus 2k, k plus 1. I can factor and cancel a k out of the top and out of the bottom. Wow, that's equivalent to just saying multiply top and bottom by 1 over k. That would mean on top, I'm going to have a k plus 2, and on the bottom, I'm going to have a 2 times k plus 1, because I factored and canceled a k. And now, folks, I'm finished, because that is exactly this formula with n replaced with k plus 1. Right? Crowd goes wild, rejoicing, dancing in the streets. It's beautiful. So this is induction when I have a nice simple formula. Okay. Now we're going to look at a slightly more complicated version to see how that would work as well. Is there any question on this one before we continue? The nice thing is when you're asked to prove it's true, it's because it was true in the first place. You shouldn't be coming up with contradictions. You shouldn't be coming up with counterexamples. If we're saying prove this formula is true with induction, we're starting with a true formula that somebody else has already derived and developed, and you're just demonstrating its truth using induction, not using examples. We just prove this is true, period, for all integers n greater than or equal to 2. That's a beautiful thing. All right. Now, what if what I have is not so much a simple formula, but more of a mathematical statement that I'm saying is true? What I mean is, what if I took something like this? I want to prove that 5 to the n minus 1 is divisible by 4. Let's see. For all integers greater than or equal to 0. What that means now is my first case is going to be n equals 0. 5 to nothing. Okay, if I take 5 and subtract 1, okay, 5 squared, subtract 1, okay. 5 cubed, 125 minus 1, okay. 5 to the 4th, 625 minus. Yeah, seems like when I raise 5 to a power, I'm always going to get an integer that's exactly 1 greater than a multiple of 4. That's kind of what you're proving right here. So 5 to the n minus 1, and by the way, you can do this with 2 to the n, 3 to the n, 4 to the n, 5 to the n. You can always manipulate that result to get some multiple. It's kind of cool. Like, excuse me, if I said 3 to the n, well, let's see, 3 to the n minus one, I know that's going to be even. I don't know if it's going to be a multiple of anything. So how do I prove this? Well, just like before, we start with our first case. Hold on, let me grab the right pen here. There we go. So let's start with n equals 0. That's our first case. You don't have to declare my first case is n equals 0. That statement right there tells me, but you notice I don't have a summation. I don't have a product. In fact, I don't even have, a totaling of things. I'm saying the value I get, the single value I get when I replace n with any non-negative integer, that value is divisible by 4. Oh, so like, where's the induction here? Well, we'll see. For n equals 0, 5 to the 0 minus 1, that's 1 minus 1 is 0. Wait a minute. Is 0 divisible by 4? Yeah, 0 is divisible by all numbers, remember? Now, on the exam, a lot of us got that backwards. 0 is divisible by all integers. No integer is divisible by 0, because that would mean 0 is in the denominator. If 0 is in the numerator, that means I have no remainder. Remember, the definition of divisibility actually has to do with the fact that there's 0 remainder. So I'm not equaling another side. This is 0 is divisible by 4. Or in other words, 4 divides 0 is another way of saying that one. All right, so we will assume true for n equal k, meaning we're going to assume that 5 to the k minus 1 is divisible by 4. Sorry, it's kind of squeezed in there. Now, how's that going to help me? Well, now let's use what we know about rules of divisibility. Use black pen. That means what? That statement right there means there exists, let's say, t in the integers such that 5k minus 1 equals 4 times t. That's what it means to be divisible by 4, that there is an integer that I can say that this is true for. Okay, now let's start with that statement right there. Now I want to show n equal k plus 1. I kind of need this statement before I continue, because when I say, all right, we're going to assume that this is divisible by 4, but then algebraically, I need something like that. I need something that I can now manipulate and replace. The statement, I have a number and it's divisible by 4. I can't insert that statement into any kind of equation or manipulation. So I need an actual, how does this translate? This is how it translates. So now this, what do I know? Well, let's start with, I'm just starting with a statement. I need to prove that this statement is divisible by 4. And the only assumption I made is that this is divisible by 4. So how do we get around this? Well, we can actually be a little bit clever. Isn't 5 to the k plus 1 equal to 5 times 5 to the k? So that means this is equal to 5 times 5 to the k minus 1. Let me erase it, okay? Well, does that help me? Well, I don't know anything about the 5k, but can I do anything with that? Well, how about if I wrote this, like this next to, actually, right here, as 4 plus 1 times 5 to the, times 5 to the k minus 1. Why would I do such a crazy thing? Because if I distribute, I'm going to have 4 times 5 to the k plus 1 times 5 to the k minus 1. Absolutely, this is equal to this. This has nothing to do with any assumption, and this is equal to this, and this is equal to this. That has nothing to do with my induction hypothesis. Okay, I'm just using simple algebra on exponents. Why is that important? Because now I can use my induction hypothesis right here. Okay. And what is that? Plus 4t. Now, you don't have to explain that 5 to the k plus 1 is 5 times 5 to the k. But if you were doing this in a textbook, you'd just say, rules of exponents. You can do something like that. But why is this statement true? This is true by my inductive hypothesis. So that's a really good one to do. Say, by the induction hypothesis, I now have this is equal to this, and I can factor. Now that is equal to 4 times 5 to the k plus t. Okay, now stare at that for a moment. Okay, so what does that mean? Well, what if I say, I don't know, what letter aren't we using yet? Let r equal 5 to the k plus t. Well, 5 to the k means 5 times 5 times 5, k times. That means I'm doing a product plus t, but t is already an integer. Then we know r must be in the integers. Why? Since integer addition and multiplication is closed. We know this. So what does that now mean? That now means, drum roll, please. Since this is equal to this is equal to 4r. Therefore, 4 divides 5 to the k plus 1 minus 1. And that was what we were trying to prove. Beautiful. Now, this one was way different from the other ones because I didn't have some formula that I just added the next term and so on. So based on my assumption, what can I create? What equation can I create? Because then that's what I'm going to substitute in later. I love this one because this is the true beauty of induction right here, is a problem of this nature. Now, it helps that you believe it's true, by the way. That's kind of critical. So my strongest suggestion to you is that you practice as many different types of problems. Don't do 10 prove the summation formulas. After the second one, they're all going to feel exactly the same. But try to do a summation, try to do a product, try to do a statement at the very least, so you get the hang of what it looks like. Then we're basically going to move on from here. But a lot of our really, really important formulas that we're going to see later on involving, for example, like combinations and factorials and things like this, induction is usually the way the formulas are proved. Not derived, mind you, but proved. Okay, now that's how far I wanted to